Right, small select audience again. Interesting. Must prefer the web stream. Alright, so I'll have a quiz out next Monday, and Jashank over the weekend will spend his entire weekend writing assignment 1. So make sure you find a prac partner. There's one group that's been formed on the website. The rest of you get onto it. Let me see. Do I have a quick way of getting there? No, I don't. Just point you in the right direction. 1315. Down here, there's groups. Go there and you can form a group. If you don't know who to form a group with, there's a group matchmaking site where you can just post comments and get in touch with each other. What else is new here? I added some of these readings, Postgres documentation that was already there, and for the lectures I finally managed to get those videos to work, so you can take a look at them, or you can just follow the link to the Echo360 site if you want to look at those. So as far as the videos go, Tuesday I'll take the videos home and do all the post-processing on them, and then I can't upload from my home because I have a quota, network quota, that I don't want to blow just with uploading a couple of videos. So I'll bring them back in on Wednesday morning and upload. So that's when they will normally be available, unless I manage to stuff something up like I did this week. Today's lecture, as soon as I've finished, I'll go back to my office, do the post-processing, and hopefully load it up later this afternoon. Any other questions about the website? Or any questions about the website? Nope. Oh, one other trick. WebCMS has a little bit of a wacky idea about forums, and you have to explicitly subscribe. So if you want to be sent messages about a certain topic or messages that are posted on a certain page, you need to go and click that little thing. So if it's dark like that, that means I'm subscribed. If I click it, it goes pale, which means I'm not subscribed. Okay, so if you're not subscribed, if someone posts a message in this, a comment on this page, and you're interested in it, you won't receive it unless you are subscribed. So anything that you're interested in, and the obvious target will be something like the prac exercises or the assignments. Make sure you subscribe yourself to those pages if you want to hear other people's questions and see my answers. Right, so today I'm going to fiddle around with Postgres a bit, just to give you an idea of how to go about things, and then start talking about the storage management section of databases, and in particular get up to dealing with catalogs, which I sort of started talking about last time, but didn't really intend to. Alright, so here's another famous database nerd. Any ideas who that might be? Wears a tie. The image quality is not great, but that's what you get from grabbing stuff off the web. It's Michael Stonebreaker. Name ring a bell? No? Yeah, obviously. It should ring a bell because he's a really well-known database researcher / system builder / entrepreneur. So for almost 30 years he was a professor at UC Berkeley. While he was there, he and his students built a whole lot of systems which eventually got commercialized, some of which didn't really survive, but hey, that's life. One of those systems was, well, I don't know if it might still be around, Illustra, but it was based on the Postgres system, which was intended to be not especially a relational database, but an object relational database. Eventually, when Illustra wasn't making money or whatever, he gave the code back to his students at Berkeley, and they built an SQL interface to the system, and that's PostgreSQL. And then that was open source, and it's just been developed since. So the original version was sometime in the early to mid-90s, so it's been around with people hammering away on it for quite a while. So all of this stuff that he did, and he's still doing stuff, column-oriented databases are a newish thing that I'll talk about later in the semester. He's been building systems for ages. Based on all of the work he's done, he finally got the Turing Award in 2014, which I talked about last time, so it's kind of like the Fields Medal, Nobel Prize for Computer Science. And he's won tons and tons of other awards. He's also written a couple of interesting opinion papers. Back in the late 80s, I think, he wrote a famous paper where he said, operating systems are a waste of time. We should just base everything on a relational database back in. And his argument was operating systems do certain things with buffering from the disk, and we'll see that in a minute, not in a minute, over the next couple of weeks, whereas and operating systems don't really know how the disk is going to be accessed in the next period of time. So they just have to make certain guesses based on how they're going to do paging and whatever. Stonebreaker said, hey, with relational databases, we know exactly what the patterns of access are going to be, so clearly we can arrange access to the disk much more efficiently than what operating systems do. So that was the basis for his argument there. He's also slagged off NoSQL databases, good on him, in the last few years. He seems to hold two positions at the moment. He's an adjunct professor at MIT, and he's also emeritus professor at Berkeley. But extremely well-known and influential person in the database community. He actually gave a talk here last year, and he has some connection with CSE, so he might even come back at some point. If he does, it's definitely worth going along and having a look at his talk. Alright, let's get back to it. So, Postgres. As with every database system, they sort of claim to adhere more or less to the SQL standard, but they all add extensions to lock you into their system. So one thing that Postgres added is the notion of attribute values being arrays of values. So there's an example of an array value in Postgres that forms a single attribute, or forms the value of a single attribute. So straight away you can see it violates first normal form. But hey, arrays are occasionally useful. And the way you define an array type is like that. So you don't have to specify up front how large the array is. And what you'll find is that basically all of these non-standard data types that Postgres deals with, the way you input them is as strings. So there has to be some kind of parsing mechanism. So when Postgres sees a value that looks like that, and it knows that it's dealing with an array type, then it can strip out all the things and put it into an appropriate internal form. But pretty much everything, obviously dates are entered as strings. When you're doing assignment 1, you'll have to implement sets of values, but they're also going to be input as strings. And they're going to look a little bit like this, but they'll have quite different semantics. So you can iterate through arrays and take the first element and the last element and so on. The next non-standard thing is inheritance. So you can actually define tables in terms of other tables. So here we've got a table S with a couple of floating points. Up here we've got table R, and I can actually create another table T based on the two of those, and it will take a union of all the attributes from those two tables. So I don't know how useful that is. Personally, I've never used it, but maybe in some contexts it is useful. You can also have functions that return tables. I don't know, maybe Oracle supports that as well, but certainly Postgres does. Maybe SQL Server does too. Right, so last time I briefly talked about Postgres stored procedures, and one thing that I pointed out was that they're all defined as strings. So when you create a function, you've got to say what the types of the arguments are. Optionally, you can give names to the arguments. You don't have to. If you don't give them a name, you refer to them by $1, $2, $3, and so on. A function returns a result type, which can be void if you don't have anything interesting to return. And then you define the body of the function as a string. And these dollar things that you see floating around are just overblown quotes. And the reason they have these type of quotes was originally they just had the normal single quote that you have for strings. And if you start writing functions that contain strings and functions that contain strings that have to build strings, you can have a sequence of 16 quotes to represent exactly what you want. So finally someone came up with a clever idea. Don't use single quotes as a quoting mechanism for functions, use some other quoting mechanism, and this $$ is what they came up with. In fact, that's a specific form of it. You can actually have dollar labeled dollar, and that's a specific type of quote, and then you can match that quote down here by saying dollar with the same label dollar. So because a function body is just a string, it could be a string in any language at all, so you have to specify what the language used in the function is. And here's the example I showed you last time. So the stuff in blue is Postgres's own stored procedure language, based pretty closely on Oracle's PL/SQL. So as I mentioned last time, this is a really stupid function, and you can achieve the same effect just by defining a view, but it serves to show you how to do stuff. So you can define local variables. This type record is a generic tuple type, and you can use it basically as a target for a query. So I'm asking a query here. Whatever query I ask, R will be effectively cast to the tuple type that's the result of that query. So in this case, we've got a table called bars. Whatever the attribute values are in bars, you're going to produce a tuple like that for each result tuple, and R will be set to that type and assign values for the next tuple in the result set. So you can iterate through the results, and then you can do things with them. Here I'm doing something really boring. I'm simply adding them to the output set, because this function returns a set of bars tuples. The other thing I mentioned last time is this use of bars here is referring to a table. This use of bars up here is referring to a data type, which is what the tuples in the table bars have as their type. Okay, so the type of the tuples in the bars table, and that's the actual bars table itself. We don't distinguish. We don't distinguish them lexically, but Postgres understands how to interpret them in context. Right, so this thing just runs through that query, grabs each tuple, sticks it in the result set, okay, without doing anything to it. You know, if I wanted to, I could certainly have done things to the contents of R, but to keep it simple, I didn't. Right, another useful aspect of Postgres is the notion of multi-version concurrency control. Basically, conceptually what it's doing, it's keeping multiple versions of the database. Every time you make a change, you end up with a new version. You might say, wow, that's going to occupy a lot of storage, but it doesn't, because it doesn't give an entire copy of the database. What it does, it tags each tuple, and this is where it does cost in storage. It tags each tuple with some information that says when was the tuple created and when did it expire. So you know, if you happen to be deleting tuples, you can set an expiry date, and any transactions that come along afterwards won't be able to see that tuple anymore, because every access to a tuple has to check the creation timestamp, if you like. It's not really a timestamp, and the expiry timestamp. And as long as the transaction that's trying to access the tuple falls within the lifetime range of that tuple, then it can access the tuple. Otherwise, as far as it's concerned, that tuple is completely invisible. It just doesn't see it. Okay? So there is an overhead cost in doing this. Every tuple has to be tagged with lifetime information effectively. But why do we bother? Because with normal concurrency control, what you tend to do is, if someone's writing on a table, you block anyone from reading that table until they've finished making the changes. With multi-version concurrency control, you don't need to do that, because even if someone's writing on the table, depending on when that process started and when your process started, you won't necessarily see the changes they're making if those changes conceptually weren't visible to you when you started. So you don't have to block readers, and you don't necessarily have to block writers either. So far less locking to make concurrency work properly. We'll talk a lot more about this later in the semester. Oh yeah, the other thing is, when you delete a tuple, you don't actually free up the space, you just mark it as having expired. And you might say, hey, well, that's going to lead to a whole lot of garbage floating around in the database, all these tuples that have expired. So the way Postgres handles it is there's a separate process that runs in the background, and every so often scans through the database and then frees up the space occupied by tuples which are no longer accessible to anybody. So it vacuums up the garbage at certain points in time. So despite the fact that multi-version concurrency control means you can reduce the amount of locking, you still can't eliminate it. So there still is some locking stuff, and we'll look at that as well when we come to talk about concurrency. One of the nice things that Postgres has that distinguished it certainly from something like MySQL was that it had a well-defined model for adding stuff to the database. So stored procedures are obviously, in some sense, they're extendable, because if you embed an interpreter for a language, then you can type strings in that language and they can become the body of a Postgres function. So when you want to execute the function, you simply invoke the interpreter for whatever language the function is written in, and that's the reason why you have to explicitly tell the system what the language is. So stored procedures are nice. The other nice thing you can do in Postgres is you can add new data types, you can add new operators, you can add new aggregates, and they're all reasonably straightforward to do. You may disagree after you finished assignment 1, but we'll see. So typically, if you're adding some of these kinds of things, you need to write some code. It needs to be written in C, and it needs to follow a particular API structure, and then you integrate that code in with the Postgres server, and then you can start manipulating objects of the new type. One important thing that you have to do, you have to write parsing functions. So when they see a value of the type, like with that array, it's quotes with braces and then a sequence of comma-separated values. When they see something like that, they can convert it into an internal form that the system can manipulate. If you're introducing a new style of index, then typically that involves introducing a new type of file structure into the systems as well. So all of this, and for indexes, Postgres defines a couple of generic indexing types that can be relatively easily specialized to create various types of indexes. So very nice extensibility model, I reckon. All right, so how does Postgres all fit together? And there's various different ways you can look at it. One is to look at how the processes interact. So you've got a client process over here that could be written in Java, PHP, Python, or it could be one of the supplied clients like PSQL. So what a client has to first do is connect to a process that's always sitting there listening for connections. Normally, you'd have to do some kind of authentication, so you'd have to provide a password or whatever. The way we've set up, or the way you're going to set up your Postgres service, we basically bypass that. So you're acting as a Postgres super user with all the stuff that you do, so you can just go straight into the system without needing to authenticate. You do need to connect, of course. So once a client has successfully established a connection through the listener will invoke a back-end process to handle whatever this client wants to do. So another server, or a server process, comes into existence, and then that server process is connected to the client. The client sends requests in the form of SQL statements, and it gets back responses in the form of sets of tuples. So you'll always find at least 3 processes floating around in a Postgres server. You'll have the listener, which once upon a time was called the postmaster, will always be there. You'll have your client, of course, and there'll be another back-end process that's serving the client. As far as memory and storage goes, Postgres makes heavy use of Unix shared memory and sets up a lot of buffer space in shared memory, and also sets up some tables in shared memory. So all of these processes can access that particular chunk. You can think of shared memory as a chunk of memory that's available to be accessed by a whole lot of different processes. So the postmaster can access the shared memory, all of the backends can access the shared memory, clients cannot access the shared memory, so they have to do everything through one of the backends. So I mentioned before that Postgres does a lot of buffering, and any database system that wants to run efficiently is going to do a lot of buffering. There's an interesting little interaction because Postgres is sitting on top of Unix or Linux, and Linux does its own buffering from the file system. So I'm not sure what the effect of the interaction there is. Maybe it just means, hey, you don't, when Postgres thinks it has to read something from the disk, it doesn't actually read it from the disk, it gets it from one of the file system buffers. And then of course we've finally got the actual storage where stuff lives permanently. Everything in shared memory, depending on the kind of memory hardware that you've got, and typically it's volatile, so as soon as your server gets switched off, everything that was sitting in here is gone. So the only way you can have permanent storage is to make sure that it all ends up on disk. And Postgres does a fair bit of work writing transaction logs and so on to make sure that even if the server crashes at some point, and your server is guaranteed to crash at some point when you write code, and compile it up and run your server. Oh dear, core dumped. So Postgres writes huge transaction logs. We'll have a look at the files in a minute. And even if the system crashes, when the server comes back up, it'll go and examine the transaction logs and reset anything that needs to be reset. And so the database ends up, even after a crash, back in some kind of sensible state. Now maybe some transactions that were happening at the time the crash occurred get unwound, but hey, it's better than having half a transaction done when the system crashes. So that's memory, and the final thing to look at is how it's all laid out on the file system. So at the top level we've got the data directory, which you're going to put on /server, or if you're running Postgres at home, it'll be somewhere in the file system of your machine. My data directory happens to be there. I just decided to install Postgres at that place. That big enough? At the back, readable, good. And in fact, I did something possibly a little bit weird. I decided to put everything Postgres related in this directory. So all of the normal stuff that gets installed, like bin, include, liblog, lib and share, gets installed there. Often they'd be installed in system directories, and then the data would be stored somewhere else, but I don't care, I'll just put it all under here. So this data directory is what I've called on the slide PG data. So if I go and look at that, I find a whole bunch of stuff, some of which I know what it does and some of which I don't. PostgreSQL.conf, that's the file, one of the files that you have to modify when you install your server, because it has to, we have to get all the environment stuff in sync, and so there's a bunch of environment variables that we'll have a look at in a minute, but the values they have has to be consistent with what the Postgres server is looking for, and that information is given in PostgreSQL.conf. And you can have options for the server. Oh no, they've changed the layout. How dare they do that? They've moved the yeah, this is probably it. In fact, they may have improved things lately. Let me just check that they haven't. Oh no, that's where the transaction logs are. Aha! Alright, change the directory name. Good on them. So when Postgres is running and when it's making changes to the database, every change that it makes gets logged in this directory, and they build up pretty big. You can see this file 16 meg. In fact, it creates the file with the default size 16 meg. But it will create multiple files like that, all 16 megabytes. And in the past I've had students saying, oh, that's wasting a lot of space. Let me get rid of those files. They're big, they don't seem to have anything useful. Trouble is, based on what I said before, when the server starts, it goes and looks for these transaction logs so that it can fix the state of the data in the database. If it doesn't find the transaction logs, it gives up. So once you've removed these transaction logs, your server's stuffed. You'll never be able to restart your server. And really all you can do is go back, reinitialize, and any data in the databases is no longer accessible. You may be able to tweak things so you can get that data back, but don't remove these write-ahead logs. Alright, so what else we got? Ooh, I didn't see. So the PGHPA conf file, probably was there, I just wasn't looking for it. Basically, sets out accessibility to the database. So you can save things like from a particular set of IP addresses, particular users can access particular databases in a certain way. So they can read only, or maybe they're allowed to modify the database. So this isn't really relevant in our context because you're running as the Postgres super user, so in theory you should be able to access any database and do anything to any database. So you can see I've got the old directory name there. So those log files live in pg underscore right ahead log. The actual databases live under a subdirectory called base, or at least it used to be. Let's hope it still is. Yeah, alright. So that's a directory, and inside that directory are a bunch of things with funny names, not meaningful names. These are actually internal IDs from Postgres, and we'll have a look at them in a bit more detail in a minute. And if we look more closely at that, that wasn't what I wanted to do. That's what I want. Where am I? I'm in data. Why is it? Oh yeah, no. That's right. It's because it's called base. So we've got /data/base. Makes sense. Alright. So all of those things are subdirectories. Each of those represents a database. And if we look inside one of them, then it contains a whole lot of files. And we'll have a look at the structure of those files in the next little while. Not today, but next week. But we may have a quick poke around in some of them. So under each database is a bunch of files that contain the data for each of the relations. In fact, each relation is represented by multiple files. And how databases decide to partition data amongst files, it's highly variable across databases. Oracle used to put everything in one gigantic file. I'm not sure whether it still does. I haven't looked at it lately. But Postgres splits things up and puts the data in relatively small files. A whole lot of relatively small files rather than packing everything into one giant file. So different databases will make different choices about that. And as it says down the bottom here, all of this stuff, or all of the stuff under the database directory, is named using object identifiers. So in theory, unless you switch it off, every tuple in a Postgres database will be allocated a unique identifier. And it's not just unique within a table or something, it's unique across the entire database cluster. And it's used for various catalog type purposes that we'll see later. Alright, so here's something that we can play with. Last time I briefly mentioned the catalog tables. So there's two catalog tables that are interesting. There's a table that tells us about databases, and there's a table that tells us about tables. In fact, it tells us about a lot of other things as well, but it has the name PG_class. So we can ask some queries on these tables. If we can find out the OIDs of the various items, then we can find the directories, and we can find the files, and then we can have a poke around with the files. So I've got this pizza database, which if you did 3311 last semester, it might bring back horrible memories from the exam. But let's see. So in fact, I'll probably get this. Oh, good. Obviously I haven't got a server running. important information there. It's telling me that it's expecting to find the socket file that it connects to. So Postgres, you can either do a local Unix socket connection, so you're always doing some kind of network connection. In this case, it's going to be a local one, or you can connect through an internet socket to a Postgres server running on some other host somewhere. Okay, we're doing everything locally, so we're going to use Unix domain sockets. So that information there tells me it's very important that you read this to make sure that's where the Postgres server, determined by PostgreSQL.conf, is looking for this file. If you haven't set up your PostgreSQL.conf correctly, then it might be looking somewhere else. And what's the default location is /share or something like that. So if you see that, it means you haven't set up your PostgreSQL.conf file. Alright, so I can start my server. I've got an alias for that. I'll show you that in a minute. I'll just go up a couple of levels. Right, so I'm back up to the top level of the PostgreSQL installation. One thing you can see, I've put the log file here, and if I do tail of log, it should tell me that the server just started. So database system is ready to accept connections, and before I came here, database system was shut down. No, it wasn't. Right, anyway, that's when I shut it down. I thought, interesting, I wonder what's right in that shutdown message. In any case, that's my log file. Now the other thing, if you look in this directory using ls-a, you can see the socket files. So as long as these things are here, that's good. Means your server is set up, and as long as your clients are looking there, then you'll be able to access the server. Of course, the easy way to check that is just to do PSQL-L. If you get back a table like that, fine. Your client can talk to your server. If, let me see, I'll stop the server again. Oops. And you can see those socket files have now gone away. If I try to access the server, it's going to give me that message, which basically indicates either there is no server running, or there's a server running but it's looking on some other location for connections. So I'm trying to connect here, the server's running over here, happily looking in /temp or somewhere for connections, and that's not where I'm looking. So those two things have to be consistent. And let's have a quick look. Right, so here's the environment file. I'm pretty sure we give you a copy of that, do we?
Give them last
something like that, yeah. Alright, so I've set this up specially for this system here. Interestingly, something I didn't notice, that in the past you used to have to bump up the maximum size of shared memory on Macs, but the latest version, or recent versions of macOS, don't seem to have that problem. Maybe they do, and if they do, that's, if you've got an older version of OS X or something, you might need to do that, or do those two things to make sure that your Postgres server can actually start. Alright, so setting up the name of the home directory, setting up where the data lives. So this environment variable PG data is important. PG host, I'm not sure that that's actually so important. Probably, or maybe it's important as being the location of the socket files. So make sure that's set up appropriately. Yeah, in fact that is important. That's the location of the socket files. Why is it called PG host? Because often you'll be connecting across the network, so you want to know which server which host the server is running on. The port number doesn't really matter here because we're not accessing through a network port, we're just going straight to the socket file, so as long as the socket file is sitting in that directory, we're fine. And other stuff, you want to make sure that you've got your path set up so you can find PSQL and PG_CTL and so on. I set up these aliases just to make it easy to start and stop the server. Notice that I put my log file in PG home. I think the version that we've given you puts it in PG data. Doesn't matter. Right, so in any case, before you do anything with your database, you've got to make sure all these things are defined, and the way to do that is to do a source. Now, if I was to go and look for, it would tell me that, which is the appropriate location. Alright, so what was I doing? Oh, that's right. Alright, so we've got a database, a pizza database, which we would have seen when we did PSQL-L. Or we would see if my server was running. Alright, so database called pizza. So I can go and look at that pizza database if I type the name of the command correctly. And I can see that there's a number of tables there. So the thing was, I wanted to find out where the data for a couple of these tables is actually stored. So the pizzas table and the people table. Now notice I've written these with uppercase letters. Postgres maps every name to all lowercase. So one context that can be annoying is if you're using camel case, if you've got multiple words. So, you know, capital THE, capital C, URRENT, capital T term. So if you use that, it all gets mapped down to lowercase and you lose the boundaries between words. So often people tend to use underscores to make sure, just for naming purposes. Alright, so there's no point me looking for a file with capital P because I won't find it. I have to look for lowercase p. So first thing, in any case, I've got to find out which directory the database is located in. So to do that, let's just quickly. So these are the columns or attributes in the PG_database file. One thing you might notice, there's no OID column mentioned here. OID is an implicit column that appears in every table. So I can go select. I could just do that for a start. And that will give me a list of OIDs and names of databases. Alright, so what I've discovered, and those numbers may look vaguely familiar, is that pizza, the OID for that database is 24567. So if I was to go back into database, I ought to find a directory whose name is 24756. So I can go into that directory. 756. Did I type it right? Am I anywhere? Am I in the right directory? Oh, 576. Goose. Alright. So it's a whole bunch of files in here. In fact, a lot of files, which is a little bit surprising given the number of tables in the database. And each table is represented by 3 or 4 files. So it's a hell of a lot more than what we had. So the other tables that are stored in here are some of the catalogue tables. So they occupy space even though you don't generally look at them. Alright, so speaking of catalogue tables, let's go back into the pizza database, and we want to find which table, or we want to find which files correspond to the pizzas table. So the pizzas table is mentioned in the PG class catalogue table. If I just do this, you can see why there's so many files. So it's not just tables that are represented by files, so these primary keys are also represented, and then we start seeing, so as well as our standard tables, we start seeing all of these different catalogue files and indexes into catalogue files. So that's why there are so many files there. Alright, now something flashed past up the top here. What were we interested in? Pizzas. So that's the object ID of the pizzas table, so I ought to find some files that mention that here, and there's only one in fact. So I thought I had an index on that. Oh, maybe that's handled by a separate thing. Oh yeah, the primary key index. So let's right, so that's the B tree index on the pizzas file. Alright, so I should have done ls-l just to prove that that's a file and not a directory. It's not very big, 8192 8K. It looks like one block of information stored there. Can I look at it? I can try, but I'm not going to get very far because it's in binary form. I ought to, however, be able to find some of the data that's stored in the database. Okay, so if you've got text fields, they're going to be stored as text in the binary database files. We'll be having a look at the actual structure of all these tuples. So these are all the tuples in the pizzas table and how they're actually represented internally or in this form is something we'll look at later. So if I hope I didn't just change that. It's an interesting thought. I was thinking of trying to change something and see if it actually worked just by editing that file. Would have been interesting. But in any case, if you want to find out what text strings are in the file, then you should be able to do something like that, and you'll see all of those names. And if we bothered to look at the pizzas table, they'd be the names of all the various kinds of pizzas. Some of which have lead characters at the front, and that's pretty much coincidence that the text string was there and there just happened to be a byte in front of the text string that also looked like that was an ASCII character. So this strings program simply looks for sequences of printable ASCII characters and dumps them out to output. Yeah, alright, so we've got one block of data in the pizzas file. What was the other one that we wanted to look at? People. Okay. So I'll have to go back into Postgres. No, in fact, why am I typing it in? Postgres has conveniently people, right? So that's the file corresponding, well, that's the OID for the people data. Just in case there are more files related to that. There are. So there's two files, and you can see this file is actually quite large, and I'll bet that's divisible by 8192. So there are 9 blocks of data in that file. What's the FSM file? I should have looked this up before I came. I can't remember. I'll describe it later on when we talk in more detail about how these files are structured. Alright, so if you really want, you can go poking around at the files to see how Postgres is representing various parts of your database. That's nice. Oh yeah, I know why that is too. Alright, so I can ask you to do something like that and you should be able to do it. Alright, so installing Postgres. Ooh, look at the time. Alright, before I start on this, let's have a break and I'll talk about some aspects of installing Postgres just to make sure that you don't have any problems with Crack 1. Alright, let's stop for 10 minutes.